this video will address two issues, stability and robustness. And what the difference of them is simply this. In this system, this is a very stable person because he stands on 2 feet. In this scenario, this person is unstable because he stands on 1 feet. What is robustness then? If I have an additional person, I push him, okay, he may actually tilt a little bit and return to stability. Alright? If I have another person over here, push you, this dude is gonna fall down. Right? And therefore, who is more robust? And as you can see some meaning to robust and stability. And therefore, stability and things like that are talking about state of a system. Okay? Which all the way goes back to state space analysis if you talk about it. And robustness is how well it can tank before it becomes unstable, which goes back to the gain margin, phase margin, right? If you still remember, and the last one, which is the vector margin, if you remember. Alright, this is the 1 over lambda distance, and then you have something like that, and then the angle is some theta. You know, if you still remember, is how much to instability or how much to instability, something like that. Robustness is something like how much you can tank before you become unstable. Alright. In other words, it's a measurement of stability. I don't know how to define in a way, but anyway, let's start. Therefore, as we say earlier, stability is talking about this, talking about the state. And if you talk about state, we're gonna talk about BIBO, meaning bounded input or output. Alright, for example, if I have a bounded input, meaning some values, if I input 5, I know that at the end of the day I would have about 10, or maybe approximately like 20. Alright, I have a bounded output, I know my values. However, if I have a bounded input and an unbounded output, this means that if I input 5, I'm gonna get infinity, then it's considered unstable. And therefore BIBO itself is somewhat this meaning of that. Alright? And asymptotic stability, BIBO stability, is simply stating this. Asymptotic is always stable. It's always stable. That's the meaning. And asymptotic is that it asymptote to 0. Alright, you may actually zoom, go on to somewhere else, and eventually it will die down to 0. Or in other words, it will decay back to 0. Somewhat of that meaning, okay, for stability, because 0, if the system dies down to 0, this means that it's stable lah. That's just the meaning in it. Now, what about internal stability? Is it, for example, if you have a certain block diagram, you're just gonna inject each of this section over here. Internally, you're gonna inject all certain inputs and see whether do they go to infinity. We're just measuring, and we're gonna put input, and when we measure, we see whether do they go to infinity or not. So we're gonna use this method of internal stability to actually test for our system for stability. Alright, and if and only if the system is internally stable, if it's a BIBO stable, okay, if it's a BIBO stable, then you no need to measure. It's because the system itself is always internally stable. BIBO stable means that it's always internally stable. Or if you measure already, or in other words, if you can first measure internal stable using the method that I've shown you earlier, or using this method, and then you can say that it is BIBO stable. Yeah. And otherwise, if you know that your system is BIBO stable, then this means that they are internally stable. That's the definition of that. Alright, so definitely, if you want to test for stability, use the internal stability. That's the meaning of that. Okay? Now, Nyquist plot. For Nyquist plot, it can help us to understand stability also. If it doesn't encircle -1. Alright, -1. Meaning, if you have a circle, this is encircling, but you're circling some other stuff. If I have another transfer function, and with a Nyquist plot like this, I encircle -1, this means that my system is unstable. Alright? Or in other words, if I were to encircle 2 times, it's also unstable. So Nyquist plot can help us to determine stability in terms of how many times it encircle -1. Alright? So just a practice. If this is the case, is this stable? And I will say that this is stable. It's because it didn't encircle -1. It didn't do that, right? It's just like that only. Okay, next question. This is the -1 radius, correct? And then we have a Nyquist plot over here. Is this stable? Yes, it is still stable. Alright, as long as it didn't encircle -1, it's always stable. So don't be fooled by the -1. Alright, so because previously I thought that it was like, you know, within this contour is considered stable, otherwise it's all unstable. No, this is not the case. Okay, and now if I should know that you already know that CP, alright, is something that deals with the S and the T, alright, the sensitivity functions or the complementary sensitivity function. So here I can represent the CP closed loop as in fact as a L. Alright, so in other words, CP is equals to L. Okay, and then we know that, alright, because if you still remember back the sensitivity function, 1/1 plus CP. Okay, if it's equals to 0, then CP is equals to -1, and then L is equals to CP, therefore L is equals to -1. This is why also here, if you remember just now why I didn't write properly, is that actually L is equals to -1. You can write L minus L, or you can write -1 also. Oh, okay, I don't want to confuse you. Anyway, this is the meaning of stability criteria. Alright, just take note that don't encircle -1 will do. Okay, ignore my minus L and -1. Okay, ignore it. Don't remember it. Okay, ignore it first. Okay, now come here. We are still talking about Nyquist stability criterion still. So if you have a single input, single output, meaning you input at one input, you output at input. So you have one input and one output, that's all. For the open loop system, this means that you have a system, I call it GS. This is one input, one output, open loop. Alright? Stable, this means that this system is stable. And that closed loop system is stable. Closed loop now is stable if and only if. So therefore, the closed loop is stable if and only if it does not encircle the point -1. Alright, so I'm just repeating myself. It doesn't encircle -1. This is the pitch. Okay, N is equals to Z plus P. This is the Nyquist stability criterion. Alright, where Z is more than 0. This is the number of zeros in the right half plane and whatever thing. Alright, I recommend you just click the link below, somewhere over here, and then you should know what is it all about, because it's a very long series of stuff. And then the link that I provided you is just some summary of it. Alright, I'll not go through it, it's just straightforward. Okay, it's not that straightforward, but at least something. Alright, never mind, I'll just go through with you now here. Okay, it will be better. Because I have no time for the robustness. Next video I'll talk about robustness, but now I'll talk about stability criterion. Okay, where Z is. Alright, I'll just briefly talk about it. It should be Z is equals to M plus P. Okay, I don't know what the hell am I writing just now back in that thing. So this is not the definition. Please remember, this is not the definition. Please please. N is not over here. Okay, this is the better explanation. Z is equals to M plus P. So what is Z, what is N, what is P? Now I'll talk about it now. I'll explain in terms of this. Alright, in the S domain I have a contour. This is a contour. Okay, S, and I call this a Nyquist contour. And this Nyquist contour is simply stating that S, you know, S is equals to sigma plus JW, the real and the imaginary. Alright, so in this contour, it deals with certain values or certain equations of sigma plus j omega and certain intervals. I'll not go through with you, but I just want to let you know that, for example, if I were to travel in this direction, clockwise direction, if I take this point, I'll plot it over here. There's maybe one point, and if I will take this point, I'm simply translating into here, and so on and so forth. In the end, alright, when I go through this contour, I will have plot a Nyquist plot out. Okay, and I'm gonna also plot in over here. You see, I'm gonna plot every plot over within this empty spaces. I'm gonna plot also within here. Alright, this is actually in terms of, we call this the mapping system. Okay, in order to know how to use, we have a transfer function g, alright, with a fake bed h. Okay, and then the closed loop of it is g over 1 plus gh. This is the closed loop transfer function. If I were to plot it out into the Nyquist plot, I would have something like this. Alright, this is 2 encirclement. Alright, in the clockwise direction. Sorry. And therefore, alright, the n is equals to 2. Okay, n is simply the clockwise encirclement of -1, okay, in the Nyquist plot. And this is the Nyquist plot. Okay, now if I were to solve for 1 plus gh and get the roots, maybe I will have maybe s plus 2, s minus 1, s minus 3. Okay, this is the roots for this. So when I solve it equals to 0, I have all this, for example. Okay, then we know that there will be one pole in the left half plane. This is the left half plane, this is the right half plane. Alright, and I'll have 2 poles in this region over here. Okay, this 2 poles is simply p equals to 2. P is simply the number of poles in right half plane of Nyquist contour, or in other words, in this contour. And why is it in the right half plane? Is because the roots of this s minus 1, if it's equals to 0, means that s is equals to 1. Alright, if you have the roots as a positive roots, this means that it's inside the right half plane. That's the meaning about it. Alright, so if you have 2 and 2 over here, you would know that there will be, because we haven't solved for this yet, we haven't solved for how many zeros are there. Alright, this is because here is number of poles in the right half plane of Nyquist contour, which is this contour. So we have to count the number of poles inside here, but we don't know yet because we haven't solved for this 0, and therefore we don't know how many zeros are here inside this plane, and therefore we are keen to find the number of zeros over here. And therefore 2 plus 2, since we have these 2 informations, we have 4. And therefore I know that I have somewhere 4 zeros within this plane. Alright? And that's the reason. Okay? If, for example, if instead of 2 poles, alright, after I solve for this poles, I have this thing now. Okay? So I have all the poles lying in the left half plane. There is no poles within this contour. This means that p is equals to 0, and 2 plus 0 is equals to 2. This means that there will be 2 zeros inside this thing. And this information can be reflected if you were to solve for the roots of the zeros over here. Okay? You get what I mean? I think you get what I mean. Okay? And if that z is more than 0, in this case is 2 more than 0, then it's unstable. And that's just the meaning of it. Alright, and just lastly is that clockwise encirclement, this means that it's going in clockwise. If it's going anti-clockwise, it's going in this direction right now. Alright, if it's going in this direction, not this, okay? If it's all going in this direction, is anti-clockwise or counterclockwise, then it's equals to -1. If there is 1 loop anti-clockwise, then it's -1. If there is 2 loops, then it's -2. Alright, if you're talking about clockwise now, just now it's counterclockwise, so it's negative. So CCW, counterclockwise is equals to negative. Clockwise is equals to positive n. Okay, I hope this is pretty clear for you. And this is the summary of what we know and what we don't know, and things like that, and the timing. And I'll reflect it inside the video description. I'll see you in the next video for robustness.